I will be talking about somewhat of a side project that Ken and I have been working on, Ken Kehoe and I, called Radar Tracking of Quality, or RadTraQ. So just as an overview, RedTrack is a Python library housing routines related to assessing, monitoring the quality and calibration of a radar. And as some background here, so when I first started with ARM, I was with ARM's data quality office, and I produced a lot of scripts to evaluate the radar data. Many of these scripts were developed in IDL, but the DQ office has shifted to Python over the years, so we've been working on porting a lot of these old scripts over to Python. We've been working on adding to it and really making it open source. And that's really where this library came from. Right now it's mainly in our free time to port this over and as needs arise. So any collaborations, contributions are greatly appreciated. And the great thing about this is that it could also directly feed into the ARM's data quality office in their processing and their monitoring of the radars, but it can also contribute to the broader community as well with what's all in here. It is a work in progress, so consider this an open invitation to everyone here to get involved if you have interest in radar data and quality. So again, it's a work in progress. So some of the things that we have in there is working with these raster corner reflector scans. So in ARM, a number of our cloud radars, our scanning cloud radars, perform corner reflector scans. We have codes in there shown on the left side here as how you can access it. But to plot up those raster scans, to do some initial statistical analysis to figure out where the center point is, where the top is, and then provide that back. It's definitely useful if we're doing these on a regular basis. You can easily process and track this information over time. So, additionally, this one's not that much of a big deal, but contour frequency by altitude diagrams, CFADs. Again, there's codes in here. Normally this is pretty straightforward, but codes are in here for calculating it and plotting it. The example on the right here is shown from roughly a week ago at our Oklahoma site with our vertically pointing radar. So it's fairly straightforward to use. A lot of this is built on the X-array data object. And we do see more interactivity between this and PieArt in the future as PieArt moves to X-array as well. Now, additionally in here, we have some codes to calculate cloud mass, and this is based off of Coleus et al. 2014, and this was a big thank you to Ian Joe at the time. Helped us ensure these were running properly on our system after we ported over to IDL at the time, and then now we've recoded it up again into Python here. But I do want to highlight one of the things we're trying to do with this, and then as I'll talk about in the ACT session as well, is we really want to use this as an opportunity to funnel citations towards these references. So in the code itself, wherever we know of a reference that we can point to, we will have a specific reference section in our code in essentially what is our header of the function. And our documentation there, and that gets pulled into our documentation online as well. So again, we're trying to point people to the references, to the papers behind a lot of this code here, to hopefully get them the citations as well. Now, using these cloud masks, you can actually do some interesting things. You can do profile comparisons. So if you're working with vertically pointing radars, you can calculate out averages from those cloud masks. In this instance, essentially, you cut out the lower level because a lot of times you get the clutter near the surface of bugs, dust, other things. So, but in this example, it does show 4 different radars here almost, but that was just for part of the example. It's actually just 2 radars, or well, 1 radar comparing 2 different modes. So We have a general mode, which is in the orange here, and then a moderate mode, an MD mode, which is in this red here. So the scripts that are in RadTraQ, essentially you can plot this up easy, by passing all this information into it, and it'll also kind of calculate out the differences as well, the average differences. So you can run the mask, get the nice clean clouds, and then do these comparisons to help track the quality of the radar over time. In this instance, we can see that there was roughly a 20 dB offset between these modes at this time. So some other things that we're working on that we're again, a work in progress. We're trying to advance when we can in the radar world. Self-consistency plots, so applying the reflectivity factor against some of the other variables, the polarimetric variables, mean Doppler velocity. For some of them, we do add in some other statistics as well. There are some equations we'd like to work in here as well, just to make sure it's lining up. But this again does give you some more information on the quality of the radar as well. In this case, we're looking at the reflectivity and differential reflectivity here on the y-axis, and we can see that there is a significant offset in the differential reflectivity, almost about 11 dB here. So it's just another way of looking at the data and trying to analyze what's going on. ZDR offsets, are somewhat in the same vein there. Looking at vertical point data, or what we call birdbath data, which is just the radar doing a PPI, pretty much pointing vertically, so it will point up and then spin, and you can get some interesting information about that on your differential reflectivity or ZDR. In that drops should look spherical when you look at them from the bottom, so you expect your differential reflectivity to essentially be near zero in those cases. So there's more we can do with those types of scans to kind of look at potential offsets based off of elevation and whatnot, so you can maybe get at if there's some pointing errors or leveling errors. But again, this is still a work in progress that we're trying to advance. But the codes to do all these plots, it's all in RadTraQ. We have the documentation up there. We have examples for most of these cases here that you can work through. There's utilities area as well, so you can get things like multi-Doppler lobe calculations. That's just come up recently, that was added. And profile extractions from volumes. Again, I believe PieArt has this in it now, or was recently added. So, looking at how we can leverage what's already there and bring that in once they kind of move to X-ray, I think will be valuable. And then we don't have to maintain the similar types of code here. So. I know this was relatively quick. This was mainly just to kind of put this out there and hopefully get some interest in this and maybe some people to come and help work on this, because it does add to what the DQ office is doing with ARM's data. So we really want to continue to add to it as time permits, and again look to the community here for additions. Also, if you have ideas, we have a long list of things on paper. We have a couple issues open already on some features we'd like to add. But if you have ideas, please go check out the repo, post them up there in the issues. This is actually under the ARM development RadTraQ area on GitHub. So, and I'll put a link up to this shortly here. But yeah, please go check it out and let me know and others know if there's interest here. So with that, I will leave it open for questions. And if there aren't any questions, we can move on into the next talk here, which.
Hey, Adam, this is Karen. I'm trying to find my hand, but I can't. So Yeah, we should talk some because we're going to be doing this new revision to Kaiser Core and Kaiser Article, and we certainly do the masking and that kind of thing. So
Yep.
maybe, and we were looking to open source some of the aspects at least of Kaiser Core and Kaiser Article. So maybe we should talk when we do the design review, certainly for Kaiser Core, Kaiser
Yeah.
Article, we should decide where to store these codes. You know, if
Yeah.
it's an ACT, RadTraQ, you know, whatever. But yeah,
Yeah.
this was real helpful.
No.
Also, Tim Wendler is looking at corner reflector scans a lot more. So maybe you and he should talk because I know he's done a lot of work with that.
Yep.
So it'd
And
be good if you could coordinate.
yeah, I've already passed on some stuff to him as
Good.
well, and we've been talking on that. But yeah, definitely let's talk more. You know, when we first started this, it was mainly just to get the codes ported over from IDL to Python and just put it out there. So if there's other ways we can help out, I'm all ears.
Yeah. If you're using the same masking as what we're using, then
Yeah.
and we do the conversion to Python, we may as well grab your code and we'll be using that instead of converting it again from IDL. So
Yeah. Yep. So much conversion these days. If we can.
yes. Great. Thanks, Adam. It was a good
Thanks, Karen.
good to hear this.
Okay.